Okay, so we've drawn out Mohr's circle in the previous class. I'm going to go and numerically work out the values from Mohr's circle in today's class here. I kind of started this yesterday with the other group. So we have some values from Mohr's circle already. So this 50 value here is the average of the y stress and the x stress. So, excuse me, 100 is the sigma x, the normal stress in the x direction. 0 is sigma y. If you take the average of those two, it's 50. And that's the center of your circle. So I might just do this over here. The center would be equal to sigma x plus sigma y over 2. So the average of them. And in this case, that's 100 plus 0 over 2 is equal to 50. All right? Now to get the radius of the circle, what we need to know is, if you look here, I've kind of marked out a right-angled triangle. We were talking about this with the other group yesterday. We need to know the length of this side of the triangle, and we need to know the height of this side of the triangle. So I'll just kind of sketch it out here again. We have the right-angled triangle like this. Now, if that was the center of the circle, this was 50 here, and this was 100 here, and the height of this point here, that was our tau xy, wasn't it? It's 125, yeah. So this is 125 this way. So the length of this line here is sigma x minus sigma y over 2. Okay? It's that would be 100 minus 0 over 2 is also 50. It just so happens that those numbers are the same because y0 or sigma y is 0. Okay, that's not always the case, but what you're effectively doing is you're taking the length of the line between here and here, between sigma x and sigma y. That's sigma x minus sigma y would be the length of that line from here to here, and you're dividing it by 2 to get the length of this line. So that's sigma x minus sigma y over 2. And then the height of this side of that triangle here, that's just tau xy. So the radius of the circle then is the hypotenuse of that triangle. So the radius equals the square root of the sum of the squares of sigma x minus sigma y over 2 squared plus tau xy squared. Or tau yx will be the same thing. It's 125 as well. Okay? So that is the square root of 50 squared plus 125 squared. That should be, we think that should be approximately 134. Let's see if we can get an actual answer for that. Well, that is Pythagoras' theorem there. It's the square root of the sum of the squares is the hypotenuse of a triangle. So, 50 squared plus 125 squared is 134.6. megapascals. Okay, so if the radius of the circle is 134.6 megapascals, then the maximum normal stress and the minimum normal stress, so sigma 1 and 2, is just 50 plus or minus 134.63. I think actually the way it's given to you on the formula sheet in the exam paper is it's something like sigma 1 and 2 is equal to sigma x plus sigma y squared, sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. But you see, that's just the center of the circle plus or minus the radius of the circle. Okay? But yeah, so that works out to be 50 plus or minus 134.63. So So sigma 1 is 50 plus 134.63 is 184.63. And sigma 2 is 50 minus 134.63 is minus 84.63. So I was out by 0.6 of a megapascal, but it's close enough. Right?
Yeah, we get that in the exam. Are we required to put that in theoretical and the...
No,
so
either or.
Done that, and we got a value of, let's say, 134 and minus 84, but they're not at 0.63. Is that acceptable?
184 and minus 84, is it?
Yeah.
Yeah, no, that'll be good enough, yeah. Yeah. They're not exactly right, but they're consistent. Do you know what I mean? Yeah. It'd be a different story now if you had drawn these on two different axes and you were getting answers that were, let's say, I don't know, maybe if you got 134 on this side, so you were out by 50, and you got, I don't know, if you were out by 50 on this side and you're out by 50 on this side because your whole axis was shifted over and you'd drawn the circle wrong, that'd be a different story. You'd be marked down on that, all right. But if you have a properly constructed circle that's done to scale and you get values that are slightly out, you'll be okay, you'll get full marks for that. Okay, so those are the kind of numerical values for that. The angle then, the 68 degrees that we measured off the 68 degrees that we measured with the protractor here, you can get a numerical answer for that as well. And basically what you need to know is the slope of this line, right? So if you get the slope of that line, you can do tan inverse times the slope of that line. We'll give you that angle. Now it's slightly different. The calculator will give you the angle measured from here down to there. So you'll need to change the sign of it based on the graph. Change the direction of that angle based on the graph. So even if you just do purely a mathematical solution, I would still always recommend you sketch out a graph just for the directions of the angles. And you'll see as well there's just two angles that have that same slope. So what is the slope of that line there? Well, the slope is rise over run or y over x. It's this height, 125, divided by this length here of 50. Or rather, you're going down 125 for every 50 that you go across. So the slope, I've left myself, I haven't left a whole lot of room here, but so the slope on Mohr circle is minus 125 over 50. Is that right? So you're going down 125 for every 50 that you go across. And that is minus 2.5. Okay? So this line has a slope of minus 2.5. For every one you go across, you're going down 2.5. If you go across 50, you're going down 125. So the tan inverse of minus 2.5 is what? If you put that into your calculator, tan inverse of negative 2.5 comes out to be minus 68.19 degrees. So not far off with the angle. But be a little bit wary, because anytime you do any inverse trig function, so inverse tan, inverse cosine, inverse sine, there's always two angles that have that answer. At least two angles that have that answer. So it's true that minus 68 has that slope, but also 120, this angle up here, from here up to here, would also have that same slope. That would be 128.2. Okay? In this particular case, that's not a problem, but sometimes it might be an issue. So again, it's always good to have even a freehand sketch, so even something like this sketch here, if I went to go tan inverse of 2.5, I'll know whether I'm looking at this angle here or whether I'm looking at this angle here. So even a little freehand sketch is better than nothing.
And what is the angle the answer to that?
Hmm?
You know the angle you got 68.
Yeah.
What's that the answer to?
That is the angle that your principal stresses are at. So it's 34 degrees back in the real world. Right? So it's the angle between your original XY coordinate system and the plane on which the tension and compression are at their maximum. All right? So that's your original XY coordinate system, that's your principal stresses there, and there's 68 degrees between them. Now the calculator says it's minus 68 degrees because they measure everything from 0 over here. But we know that it's actually, we're measuring from that x coordinate up to the horizontal axis here, so it's 68 degrees clockwise from our original xy coordinates to the principal stresses. Okay?
Will this be a full question on the exam?
Probably, yeah.
And just looking at passing exam papers.
Yeah.
Does it stay in Mohr circle, or do you know to use Mohr circle?
It will typically say plot Mohr circle and then either graphically or mathematically. There might be some cases, there might be the odd question where it doesn't, and there's the odd question where it's maybe 3/4 of a question rather than a full question, if it's an easy one. You know, if you're given the shear stresses and you're just asked for the principal stresses, that might be half a question or 3/4 of a question. If you have to work out, you know, if you're given a shaft with a bending moment on it and you have to work out sigma x and sigma y, that'd be a full question. Or, you know, if there's something a little bit more involved in it, it would be a full question. All right, we'll finish this out here and get on to the next one then anyway. So that's the slope there is 68.19 degrees, or the angle rather. Tan inverse of the slope is 68.19. So the calculator says it's minus 68.19, but from your original xy to the principal stresses sigma 1 and 2 is equal to 68.19 anti-clockwise. Okay, so that would be your answer. So the question might say something like, calculate the magnitude and direction of the principal stresses. Magnitude of the principal stresses would be 184.6 and minus 84.6, and the direction is 68.19 anti-clockwise from xy to sigma 1. Okay? The magnitude and direction of the shear stresses then. And direction of tau xy, or tau max rather, tau max. So what is the magnitude of the maximum shear stress here? So looking at Mohr circle. What is the maximum shear stress? Whereabouts on the circle is the shear stress at its maximum? No, so the shear stress is at its maximum at the very top of the circle or the very bottom of the circle. So it's maximum clockwise up at the top and it's at its maximum anti-clockwise down at the bottom of the circle. And what's the value of that? I know we've written onto the circle here now, but the value of that is just the radius of the circle. It's 134.6. Okay? So mathematically you would work that out, and we already have worked it out, but it's the radius of the circle. Tau max is equal to the square root of sigma x minus sigma y squared, sigma x minus sigma y over 2 squared rather, plus tau xy squared. We've already have that worked out, but that's the square root of 50 squared plus 125 squared is 134.6, wasn't it? But I mean, we already have that worked out in the previous page here. That's your radius of your circle, is tau max. The angle that occurs at is going to be 2 phi is equal to 90 degrees minus whatever 2 theta is. So the angle phi, well, 2 phi is equal to 90 degrees minus 2 theta. So 90 degrees minus 68.2 degrees, something like that. So that is 21.8. I think it estimated 22 off the protractor. So phi, then the angle that the shear stress occurs at is half of that, so it's 10.9. Okay, and that's it. That's the answer to that part. Okay. Now, the question may or may not ask you to sketch out the stress elements for those as well. And that goes back to your question, Derek, and is it a full question or not? It depends on how much you're asked to do. If you're asked to plot out stress elements for each one of those stress states, sigma 1, sigma 2, and tau max, there's a bit more work in that. So that would probably be more towards a full question. Yeah.
And creep is on the exams.
Usually there's something to do with viscoelasticity, yeah. Yeah, so it could be creep, it could be stress relaxation. Some years I would have focused more on experimental creep curve data. You have your creep curves and you can take a constant time section through them and get an isochronous stress strain curve, or you can take a constant strain section and get an isometric stress relaxation curve. Some years I focused more on that, and I would have given them a set of creep curves in the exam. This year I didn't focus a whole lot on that, so take from that what you want. All right, I think that question is done out anyway here. So we worked out the magnitude and direction of the principal stresses and the magnitude and direction of the maximum shear stress, tau max. Okay, stop that.